Hello students, today we are going to deal with experiment number 4, half adder, full adder and 4-bit parallel adder by using the ICs 7404, 7408 and 7483. Okay, in LT Spice we are going to simulate this experiment in LT Spice. And we know that this is an arithmetic circuit. Half adder, full adder and 4-bit parallel adder are all arithmetic circuits. Okay, so half adder is a 2-bit adder, whereas full adder is a 3-bit adder, and consecutively we are going ahead with 4-bit parallel adder also. Okay, parallelly you are going to add 4 bits at a time. Hence it is said to be 4-bit parallel adder. Okay, let me come with arithmetic circuits. The first circuit, generally arithmetic circuits are classified into two types, namely adder and subtractor. Here we are going to deal only with adder. Okay, so half adder, namely two types, half adder and full adder. Adders of two types, half adder and full adder. So 2-bit adder, so you will be having two inputs A and B, so that you will be having 4 possible input combinations. You will be having 4 possible input combinations. Okay, right. So we know that in digital circuits you will be having only two bits, zeros and ones. So 2 power 2 combinations, you will be having 4 possible input combinations in the 0 0 0 0 0 1 1 0 1 1. Okay, so if you add these two bits, 0 plus 0, sum will be 0 and carry will be 0 again. Okay, sum will be 0 and carry will be 0. 0 plus 1, sum is 1 and carry is 0. 1 plus 0, sum is 1 and carry is 0. 1 plus 1, you have 2 in decimal. If I need to convert this in binary, I'll be writing it as 1 0, where this is sum and this is your carry. So 0 is your sum, carry is your 1. Okay, so after drawing the truth table or after deriving the truth table, you need to design the circuit. Okay, so for implementing the logic circuit, we will go ahead with K-map. For K-map, so this K-map, since you have only 2 bits, you have 4 possible input combinations. So K-map is nothing but A, B, 0, 1, 0, 1. Okay, so in that fill the table. What is the min terms? Min terms are nothing but here 0, 0 is said to be M0 and this is M1 and this is 1, 0 is M2 and this is M3. Okay, of this min terms, because this is 0, 0 is M0, M1, M2, M3. Min term will always be represented by small letter and it's a product term. It is the product term. Namely, this is A bar, B bar. Okay, this is A bar, B, and this is A, B bar, and this one is A, B. Okay, so now how we are going to represent this? So let me fill this K-map first. So first we have two possible inputs A and B, and you have two outputs, which is that sum and the carry. So sum, in the sum, look at the sum column alone. In the sum column, for 0 1 you are getting 1 and 1 0 you are getting 1. For 0 1 I am getting 1, I have built up 1, and 1 0 we are having 1. And if you see this, you have only diagonal ones. So let me write the sum first. How can I write this? Because I cannot combine. Only the neighboring cell or the adjacent cell I can combine in K-map. Okay, that is in 2 power n combination. That cannot be possible here. That is not possible here. So let me write it here. A B bar plus A bar B. Okay, if you take this out, it is A XOR B. A XOR B. Okay, A XOR B. What is A XOR B? What is XOR gate? For dissimilar inputs, you will be getting 1. So this can be implemented by using an XOR gate, meaning either of this combination is occurring at the input. If this combination is occurring at the input, for both the cases, your output will be 1. Okay, for either of the cases is appearing at the input and the output, sum output is 1. So you can implement this by using your XOR gate. Next, go ahead with the carry. What is a carry? Carry, look at the carry output column. Here you have 1 for 1 1 combination. So here you just write it down 1. In the carry, you cannot combine anywhere. So I can write only the carry as AB. Okay, write the carry as AB. So now how to implement this using your logic gate? Okay, using your logic gate. So let me implement what we need two possible inputs A and B. Okay, we need two possible inputs A and B. First, sum can be implemented by using an XOR gate. So we complete this with an XOR gate. So 7486 is an XOR gate. And carry can be implemented by just simply AB. It's an AND gate. It's an AND gate. So this can be implemented by using the IC 7408. Okay, 7408. And look at the transitions here. What is the transition? A is taking for each transition in the sense for each combination of input from one input to another input, always try to make it as 1 millisecond, such that each transition is happening within a millisecond. Okay, assume like that. So now A is taking the signal A is taking first 2 0, okay, 2 0, and then it's taking 2 1. It is taking 2 1. And again it is going to take 2 0 and 2 1. This is what the input combination is. So this 2 0, as I said, for each transition it will take 1 millisecond. So we have two different combinations. So let me take 2 milliseconds because it is two boxes here. So 2 milliseconds off and 2 milliseconds on time. Similarly, take for the B. So B, if you look at the table B is having 0 1 0 1. So B, if I draw B, so 0 1 0 1. Okay, like this it goes on and on. Okay, so let me take this is 1 millisecond and this is 1 millisecond. Okay, the total time is nothing but 2 milliseconds. Similarly here the total time is nothing but 4 milliseconds. Okay, so initially you have this 0 and then you have 1 for the input combinations. For this input combinations we need to try in LT spice and we need to check the output whether your truth table is verified or not. Okay, let me go ahead with the full adder circuit. Full adder circuit, it's a 3-bit adder. So A, B, C, N, it's a 3-bit adder. You have 8 possible input combinations because 2 power 3 is 8. From all 0, 0, 0, 0 till all 1, you will be having this many input combinations. Again, you will be having two outputs, namely the sum and the carry out now. Okay, so since there is a carry out, I will be taking it as C in, carry in. So how will I add? We already know from half adder. So 0, 0, 0. If I add, I will be getting sum 0 and carry 0. And for a combination of 0, 1, I will be getting 1, 0. Okay, for input combination with only 2 ones, I will be having 0, 1. Let me fill this up here. So for a combination of 0, 1, 1, 0. For a combination of 1, 0, 1 or 1, 0, the combination output combination is 1, 0. Again for 1, 1, you will be having 0, 1. And you have only 1, 0, 0, so it is 1, 0. 1, 1, 0, 1. And 1, 1, 0, 1. Now 1 plus 1 plus 1 is 3 decimal. If I take binary equivalent 1 and 1, meaning sum is 1 and carry is also 1. Okay, sum is 1 and carry is also 1. Sum is 1 and carry is also 1. So these two are 1. Now what is the next step? Step 2 is nothing but we need to go for the K-map, because we need to realize this full adder circuit in the LT spice. So how many inputs? You have 3 inputs. So you should have in the K-map, you should have, it's an 8 variable, 3 variable K-map with 8 possible cells, possibly input combination cells. So A will take 2 values 0 and 1, and B and C can take 0 0 0 1 1 1 and 1 0. Okay, 1 1 and 1 0. So now what is that we need to do? We need to fill this table up. Okay, we need to fill this table first, for which are all the combinations for 1 2 minterm 1 2, because these are all the minterms. I hope you know this, because this is 0, this is 1, this is 2, this is 3, this is minterm, I'm writing it down, this is 4, this is 5, this is 6 and 7. Accordingly, you fill this minterms wherever your output, for which minterm your output is 1. For this minterm, namely 0 0 1, your output is 1. For 0 0 1, your output is 1. I have written here. Okay, and then for 0 1 0, your output is 1. 0 1 0, your output is 1. And then come again here, 1 0 0 1 0 0, your output is 1. And then 1 1 1, your output is 1. Okay, it is being filled. See, here you have 1 and here you have 1. You have neither of the neighboring cells. You cannot combine 4 ones here. You cannot combine 4 ones here too. Is it okay? Okay guys, after filling this up 1, okay, after filling this up 1, what is this happening? We need to reduce it. We need to, here you go. We need to reduce this. Check for the possible value combinations, but we cannot reduce here in the sum. Why? We have only diagonal ones here. So let me write the expressions for which are all combinations you have 1. We know the minterms m0, m1, m2, m3, m4, m5, m6 and m7. So how will you write sum? Sum is nothing but for which combinations you have 1, m1, 2, 4 and 7. So m1, 2, 4 and 7, you have your sum to be 1. Okay, then come I will tell this how to reduce this expression for sum in the next slide. Let me complete this C out. Okay, C out for which m3 is 1. Okay, so this is minterm again, this is 0 1 2 3 and 4 5 and 6 and 7. So for 3 5 6 7, 3 5 6 and 6 and 7. Okay, 6 and 7, 3 and 5, you have made it 1. So look for the possible combinations here also. So this is the first combination. The first one is this one. Okay, this one. Okay, and then the second one, you can combine these two ones. You can combine these two ones. And the third one, you can combine these two ones, so that all possible 1 combinations can be combined. So with that in mind, so whichever is common minterms, please write it down. For the first case, this is this one. Let me go ahead. This one is 1, BCN is done. And here for both the 1 combinations, A is common. So the other one is here left out a CN. So ACN. And here it is again A, B. So A, B. This is how we will be writing the expression for C out. Okay, this is how we will be writing the expressions for C out. Now let me check how to minimize the expression for your sum. So sum, already we know that m1 plus m2 plus m4 plus m7. What is m1? It is a bar b bar cn, and m2 is a bar b cn bar, and m4 is a b cn bar, and m7 is a b cn, because we know the possible input combinations. This is 0 0 1, and this is m2 is 0 1 0, and this is 1 0 0, and this is 1 1 1. Am I right? So now here, whichever is highlighted in yellow, take C in common from the yellow one. Then it is A bar B bar plus AB plus take C in bar from the rest. So C in bar into A bar B plus A B bar. And this is again an XOR, right? This is again an XOR. If you look this, let me take this expression, okay? A XOR B, and this one, this is X NOR, the complement of this X bar. So A X NOR B. Let me take A XOR B as X. Since X NOR is the complement of this one, so I can write it as X bar. So C in X bar plus C in bar X, which is equal to, it is again, if you look this up, it is again in the form of A B bar plus A bar B, which is nothing but your XOR gate combination. So C in XOR X, I can write it as C in XOR of what is X? A XOR B. So A XOR B. So sum can be implemented by using this combination A XOR B XOR Cn. Okay. So now implementation, we know how we need to OR gate. First OR gate, A B is the input, A XOR B. For the second XOR gate, Cn is the input. So A XOR B XOR Cn, that will be your sum. Whereas AC, BC and AB will be your for your carry if you sum this up. So this is BCN, this is AB, and this is ACN. And if I use an XOR gate here, okay, you will be getting my carry out. You will be getting the carry out. So 7486 and 7408, I think 7432. Okay, we can implement this by using these three ICs. Okay, okay, let me come ahead with the signal description that we need to use in your LT Spice. Look at the inputs. Okay, look at the inputs. You have 40 and 41 for the A, and 2021 for the alternatively for your B, and 0101 for the C. What I said, for each transition you take 1 milliseconds. So for A, so 40, 1, 2, 3, 4, 0, and 1, 2, 3, 4, 4, 1. Okay, and come ahead with B. Okay, 20, 20, 21, 20, 21. Okay, and C. C is nothing but 10, 11, 10, 11. Okay, so 1 millisecond, each box is 1 millisecond. So total time is 2 milliseconds. The screen is freezing, please wait. Hold on. Yeah, this is 2 milliseconds, and whereas this is on time is 2 milliseconds, off time is 2 milliseconds, and total time is 4 milliseconds. Whereas this one is 4 milliseconds maybe, off time is 4 milli, on time is 4 milli, total time period is 8 milli. Okay, 8 millisecond. This is problem number 2. This is the second experiment that you need to do. I mean, second part subdivision you need to do in LT Spice. Next, we'll go ahead with the 4-bit parallel adder. Okay. At a time, if we have two numbers, let me assume that if we have two numbers, two 4-bit numbers, okay, A and B, such that, let me write the bits as A3, A2, A1, A0, and B3, B2, B1, B0, which is, let it be 1, 1, 1, 0 and 1, 0, 1, 0. Okay, for example, if I need to add these two, okay, if I need to add these two numbers, so here you will be having 0, 1 plus 1, 0, 1, 1 plus 1, 0, 1, 1, 1, 1, 1 and 1. So you have a carry out, and your result is 1000. Okay, this is your result or your output. Am I right? If I need to add two bits parallelly at a time, if I need to add, whereas your half adder and the full adder and all, it is not a parallel adder. It can add only one bit at a time. It can add only one bit at a time. This is nothing but parallel adder. All at a time you can add 4 bits of two components A and B. Okay, this can be implemented. The circuit diagram is this. For example, if we are adding n number of 4-bit numbers, you will be having a carry, right? You will be having a carry. This is the first number. If I want to add 0 1 1 0 with this result, we have a carry also. So that also you have to consider when I'm adding this 0 1 0. So what is this? So this is 0, this is 1, this is 1, and this is 1 again. What is this? You need to bring the carry out of the first thing as a carry in. So what should we do? So 1 1 1 0 plus 1. Okay, 1 1 1 0 plus 1. How should I consider this is? Okay, let me repeat. How should I consider this is? Let me take the third number. Okay, the result output is nothing but O, which is O3, O2, O1 and O0, which is nothing but 1 0 0 0, and C out we have 1. Okay, this will go as Cin for the next bit addition. For example, if the next bit, let it be D. Okay, D, which is nothing but D3, D2, D1, D0, which is 0 1 1 0, if it should be added with the previous sum. So this has to be considered as Cin again. So Cin also has to be added. So 1 1 1 and 1. Your output is 1 1 1 1. Your output will be 1 and 1 1. So here we have to consider one bit called Cin bit. Initially it is 0. The first time it is 0. A1 B1 I am adding, A2 B2, A3 B3, and A4 B4. This is all from the least significant bit to the most significant bit. Okay, and for each adder. Okay, now it's see, this is a full adder. This is a full adder, because you are going to add A, B, C in. You have a sum and the carry. Okay, you have a sum and the carry. So you need 4 full adders for doing 4-bit parallel addition. So sum and the carry. The carry of the first least significant bit should be the carry in for the next most significant bit. Likewise, each carry will be connected to the next C in. C out is connected to C in. Finally, you have only one carry out. Okay, so C out. So what is your result? Result will be sum 1, sum 2, sum 3, sum 4, C out, which is nothing but, as I said, it is O0 output, O1, O2 and O3. This can be implemented by using the IC 7483. See here, this is a 4-bit parallel adder, 7483 IC. You have first number A0, A1, A2, A3 can be added here, and the second number B0, B1, B2, B3 can be added here, and Cin will be the first Cin that can be given here, and you will be getting the summed output, which is a 4-bit output number, and you have a carry out. This is how your IC will be. Okay, so now you need to give this also in LT-Spice. You need to design the circuit also in LT-Spice, and you need to do the simulation. So how we can do? Let me have, as I said already, let me have 1110 and 1010. 1110, 1010. Let me take a C in. This is A and this is B. Let me take carry in is also 1. So if you add these two number, 1110, 1010, carry in is also 1. So that should be added to the LSB first. So 1 plus 1 0 plus 1 plus 1 0 plus 1 plus 1 plus 1 1 and 1. So the output will be 11001. So this will be your carry out. How you will be giving in LT-Spice? and we know that the logic 0 represents 0 volt in analog value, okay, in voltage value, and logic 1 represents 5 volt as an analog value, okay. Let me do this and show it to you.